All right, hello everyone. This is the MA 261 exam 2 of 2019. Okay. Question 1, find the maximum value of the function f of xy equals 8x minus 6y, subject to the constraint x minus 1 squared plus y squared equals 1. All right, whenever you see like some constraint being like equals specifically, not just like less than or equal to, you're just gonna think, oh, Lagrange multipliers. That should just be the dead giveaway. So we're going to set up our kind of equation. F equals some constant lambda. Sorry, the gradient of F equals some lambda times the gradient of G. Uh, Functions here are not too bad. So gradient of F is going to be just 8, negative 6. And then gradient of G is going to be 2x minus 2 and then 2y. So that's actually not bad. But we set up our equations. We're just going to get a system. We're going to get 8 equals, I'm just going to multiply up the lambda just to make things a little bit easier. So 2 lambda x minus 2 lambda. And then we get negative 6 equals 2 lambda y. And now there's like many ways you could go about solving this. Um, you could, I don't know, solve for lambda and then set them equal to each other, or you could solve for the variables x and y and then plug them into right here. I think that makes most sense because you'll get a concrete value of lambda and then you can just go from there. So I'm gonna go ahead and do that. First, let's solve for x and y over there. I'm gonna divide by 2. We're gonna get 4 equals lambda x minus lambda, therefore, um, 4 plus lambda all over lambda is going to be equal to x, and that is just, let's see, that is 4 over lambda plus 1. Okay. And then y, similarly, is going to be negative 3 over lambda. All right. So let's plug in our x and y into our constraint. We're going to get 16 over lambda squared because the 1 cancels out, and then plus 9 over lambda squared. That's equal to 1. So hopefully you can see that's equal to 25 over lambda squared. Therefore, lambda equals plus or minus 5. So we have the value of lambda. We're not done yet. We have to find our the actual maximum. So we can plug it into our x and y values and find it for each of the values of lambda. Or we can just say, oh, hey, our function has like positive x contribution, like 8 times x. So that's a positive contribution, and then a negative y contribution. So we want y to be as negative as possible and x to be as positive as possible. So if we take the positive lambda, we're going to make x positive and y negative, and that's exactly what we want. So let's take the positive 5 lambda. So we're going to get x equals 9/5, and then y equals negative 3/5. So we're going to get f equals 8 times 9 over 5, or 72 over 5, and then minus a negative plus 18 over 5, and that is 90 over 5, or 18. And that is answer A. Nice. Question 2, evaluate double integral over the region R, um, x squared y over 2 plus x cubed. X is going from 1 to 2, and y is from 0 to 4. All right. This is kind of your standard rectangular integral. Don't even think you need to draw out the regions. It's pretty, simple, I'd say. So let's kind of draw out the actual bounds. 2 plus x cubed. We're going to get dy, or dx dy. It doesn't really matter in this case, but we'll go 1 to 2. Y is from 0 to 4. All right. So something that's, I guess, maybe helpful is that you can see like the thing you're integrating is you can like break it up into 2 parts. So like one of x and one of y. And like the bounds don't depend on the previous integrals. So say you had something like 2y, then you can't do what I'm about to say because when you integrate x, like the first one, you're going to get some value of y in it. So like you can't kind of split up the integral. But if it's like constants like this, you can. So we can rewrite this as integral of 0 to 4 of just y dy times the integral from 1 to 2 of x squared over 2 plus x cubed dx. So that looks like an 11, I can't lie, but let's go ahead and make that a 4. Okay. So first integral, hopefully it's pretty easy. Y squared over 2 from 4 to 0, or just 8. And second integral, maybe a little bit harder, but I'm seeing some sort of chain rule action going. Like we have an x cubed and then we have an x squared. That's one less power. So I like the guess and check method. Let's just guess it's some ln 2 plus x cubed. I think that's a pretty good guess. We take that as our integral guess. If we differentiate, we're going to get 3x squared over 2 plus x cubed. And that's pretty much exactly what we have here, but times 3. So if we just divide by 3, we should get our proper integral. And that's exactly what u sub is doing anyways, like behind the scenes. So if we evaluate this, we're going to get ln of, I guess I'll factor out the 1/3. So 1/3 times ln 2 plus x cubed, where x is 2, we're going to get ln of 10, and then minus ln of 3. And don't forget, definitely remember that we have to multiply by 8. So we're going to get 8/3 times ln 10 minus ln 3. Nice. So that is answer C here. And I'm pretty sure that E is also a valid answer. I'm 90% sure. It's based off log rules. Um, but I would just honestly go for C here. They probably won't do this in the future, but I don't know. It's uncertain. Question 3, evaluate I equals integral 0 to square root 2 pi, y squared to 2 pi of y cosine x squared dx dy by switching the order of integration. Very nice. So I'm going to draw out the bounds, or like the region. So x is going from y squared to 2 pi. So that's x equals y squared, x equals y squared. And then let's just do our 2 pi like this. Pretty standard. X equals 2 pi. And then y is going from 0 to square root 2 pi. That's exactly like this thing right here. So that's perfect. Y equals square root 2 pi. Cool. So this is our region. But we're going to have to do dy dx instead, because right now it's not exactly evaluatable. So we're just keeping y cosine x squared. Now it's dy dx. So y is going from, let's see, 0 to, we have x equals y squared, so we want y equals something. So y is just going to be square root x from this thing right here, if you square root both sides. X, I mean, we already have it kind of drawn out. X is 0 to 2 pi. All right, and let's go ahead and do this. So if we evaluate the integral, we're going to get y squared over 2. I'm going to factor out that 1/2 and just get y squared cosine x squared from square root x to 0. And that is, of course, dx. That is going to be, keep the 1/2, just 0 to 2 pi now, of x cosine x squared. Of course, dx stays. Um, I'm going to use the guess and check method again. I think sine 2x, or sine x squared, sorry. It's a good guess. If we have that, if we differentiate that, we're going to get 2x cosine x squared. And that's almost exactly what we have here, but just it's multiplied by 2. So if we divide by 2, that's going to be our proper integral. And don't forget, we have to divide by actually 4 because we already have the 1/2. So we divide by 2, and then we multiply by 1/2. And then we evaluate that from 2 pi to 0. Remember, sine of 0 is 0. So that is just equal to, it's interesting, sine of, whoa, 4 pi squared over 4. And that is answer D. It's an interesting answer. Can't lie. Question 4. Let D be the solid region bounded by the planes x equals 0, z equals 0, y equals x, and x plus y plus z equals 2. And it's saying which of the integrals is equal to that triple integral of the region D. So I think really I mean, I'm looking at the answers. We have all dz, dy, dx. So really the bounds are going to be the only like hard part I am to say. But Yeah, so it's going to be a little bit difficult to kind of draw it out, but this is going to be my x equals 0. C equals 0 is just the xy plane. Y equals x is kind of this line right here. I'm going to use a different color just to make it a little bit easier to see, but it's going to look something like that. It's kind of coming out. It should be like parallel to the z-axis, but I think it's pretty hard to draw that, but I'm trying my best here. Um, and then x plus y plus z equals 2 starts here and then kind of goes down like this, kind of making a triangle looking thing. But after all, it is a plane. It's just easier to draw it like this just because that's the region we're concerned with. Anyways, okay. So, um, really what we're concerned with here is um, kind of this, like the green region right here is the base of what we're integrating, and then I don't want to put blue over it because it might make it, I don't know. I don't think that helps, but we're integrating from that green region on to the blue triangle if it were like solid. So dz is first. Clearly, we're going from 0 to 2 minus x minus y because we can just rewrite this equation in terms of z. So A and E are just not correct. And then now we're focused on the green region, so that's z equals 0. So now we have just x plus y equals 2. So y equals 2 minus x. And in fact, that's our going to be our top bound, um, because clearly we can see like this thing is more far in the y direction. And it's interesting because D is our only answer here. That satisfies that. B is not going to be correct just because it starts at 0 when clearly we're starting at the red line y equals x. Um, but C is wrong because of this 1 here. That's pretty interesting that they even, I don't know, gave us the 2 minus x just like that. But very nice. Question 5, evaluate the integral 0 to 2, 0 to 4 minus x squared, square root x squared plus y squared to square root 2 times quantity x squared plus y squared, dz, dy, dx, using cylindrical coordinates. I mean, who would have thought, right? Like cylindrical coordinates, and we have all the x squared plus y squares. But I digress. Okay. So the x and y kind of bounds are going to be, we have y like that, um, and then x is 0 to 2. So we're just concerned with this portion of the um, or like the circle, I suppose. Top half of the circle. So we write out our cylindrical integral. Our outer bound is theta. So I guess I could just write dz r dr d theta. Our theta is 0 to pi over 2 because as we drew in the top right here, our r is of course 0 to 2. Is it? Yeah, it is. I shouldn't question myself. Um, yeah, because this circle right here is of radius 2, and then our z is our, I guess, only plug and chug. We're just plugging in r squared for x squared plus y squared, so we're having square root of r squared or just r. So lower bound r, top bound, uh, let's see, just square root 2r squared or r square root 2. I think it's better to write as square root 2 times r, but it is your choice at the end of the day. Um, okay. So our integral, I think the hard part is just now evaluating it really because it wasn't too hard to find the bounds. But let's see, I want to make this smaller. Oh, look at that. All right. So I see one thing. Um, Theta is not dependent on any of like the internal components or like the bounds. So we can just take out that pi over 2 and multiply by that at the end. That just makes things easier. So I'm going to rewrite that as just pi over 2 times the integral 0 to 2 times the integral 0. Sorry, inner should be an r and square root 2r dz dr. I'm forgetting the r. dr. Okay, great. And dz isn't too bad. We're going to get pi over 2, keep the outer integral 0 to 2. So we could write z, but I mean, we have some constant, so I know it's just going to be the top bound minus the bottom bound. So we still have the r inside though, so let's keep that square root 2r minus r, and then that's all dr. Okay, we could do it multiple ways. I think I'm just going to multiply out by r. That'll be easiest. We are at pi over 2 times 0 to 2 of, that's a little small. I want to make that a little bit bigger. Let's see here. Okay, that is a little bit more to my liking. Okay, it's not the best. 0 to 2, square root 2r squared minus just r squared. All right, not too bad. We could actually factor r squared out, and I think I will do that. I think that will make things a little bit easier. We're gonna get, I'm gonna keep the dr here, just like that. Okay, so we are at pi over 2 times r squared factored out. We're gonna get square root 2 minus 1, and we're still integrating 0 to 2 of r squared dr. All right. Okay. Um, Integrate r squared. We're gonna get just uh keep the outside, so square root 2 minus 1 times r squared. R cubed now, sorry. I wrote cube, but I said square. That's interesting. From 2 to 0. And that will just be 8 over 3. So 8 over 3, the 0 drops out, times pi over 2, square root 2 minus 1. We can cancel that out, so we're just at 4/3 pi times square root 2 over 1. And that is answer B. Okay, I am re-recording this question because someone walked in my room and it was not very uh, helping to my explanation. But question 6, by converting the integral -1 to 1, negative square root 1 minus x squared to square root 1 minus x squared. And I will stop reading this question because it is way too long. And it's saying we want to convert that to spherical coordinates. And again, that's just like the standard spherical integral. And it's asking for BC over A, which A, B, and C are like the bounds of the spherical integral. Okay, so I'm looking at the bounds. The A value should not be too hard because um, looking at our dy dx, our x and y bounds, that's what's going to govern our theta value or our A. So if we draw out our kind of xy plane here, we really just have a circle and we're going all around. We want to get that whole circle. So naturally, that's going to be 0 to 2 pi. So A is going to be 2 pi, and that's also reflected by that lower bound of 0. Okay, not too bad there, but let's go ahead. I'm looking at our C value, or the top bound for our rho value. Um, Again, it's starting at 0. They're all starting at 0, so that's something to keep in mind. But if we look at our Z bounds for our like regular integral, our top bound is going to be some sort of if we square both sides, we're going to get like z squared equals 4 minus x squared minus y squared, and that's just a sphere of radius 2. And then we can square both sides again. For the lower bound, we're going to get some sort of z squared equals 3x squared plus 3y squared. And maybe you see, maybe you don't, but this is just a cone, but it's going to have some sort of different angle looking thing. But it's still a cone. So to kind of think about this in the 3D axis, we have our cone. Yeah, pretty good drawing, actually. I'm kind of happy with that. But yeah, and then we have our sphere, and of course, that's a pretty weird sphere, but yeah. The cone goes like infinitely, so maybe I should draw my thing like that. Yeah, cone goes forever, forever to infinity, but the sphere does not. So if we think about rho, it's a 3D distance from like our origin. So like this is our kind of 3D distance. It's not governed by the cone at all. It's governed really just by the sphere, nothing else. The cone is going to govern our C value, but we're going to deal with that later. So our rho value naturally should go from 0 to whatever our radius of our sphere is, which is 2 in this case. So our C value is just going to be 2, um, because that's what we need to cover all this region right here. Okay, fair enough. And then phi value. Um, Many ways to do this. I think the easiest way is to look at the lower bound right here and say, okay, maybe we can rewrite x squared plus y squared in terms of r. And maybe that's what they're hinting because they kind of factored it out already. I don't know, but uh, we have some z equals uh, square root. I'm going to rewrite x squared plus y squared is r squared. So 3r squared, and that is just square root 3r. I'm not really dealing with the plus or minus because it doesn't really matter in this case, but yeah. Um, so now we can kind of rewrite this in the RZ plane. And the reason we can do this is because um, we're going to take care of like the theta anyways later. So we can just kind of generalize R this way. Um, but yeah, we have our RZ plane. So if we kind of draw out our line, because Z equals square root 3R at the end of the day is just a line with slope 3. So we have something like that. And this is going to be our like line, I guess. But if we draw it like or mark, this is square root 3. I'm going to make it a little bit bigger. This distance right here is square root 3, and this is just 1. And remember that this thing right here is our phi value. We can use some trig and find that out. So I guess tangent works best here. So tan phi is going to be equal to 1 over square root 3. So I mean, jogging my memory here. Uh, it's either going to be a pi over 3 or pi over 6. Uh, So tangent is sine over cosine. So it is going to be pi over 6. Uh, and reason is, I know sine pi over 6 is 1/2, and cosine pi over 6 is root 3 over 2. And we cancel out the 2's, so we just get 1 over root 3. So our b value is going to be pi over 6. Nice. So finally, bc over a is going to be pi over 6 times a, which is 2 pi. No, I did that wrong. Yeah, I did BA over C. Okay. Uh, C is 2, and then all over 2 pi, 2 pi. So we have 1/3, or pi over 3 over 2 pi, or just 1/6. Cool. That is answer E. All right. Question 7. Find the volume of the solid region enclosed by the surface rho equals 12 cosine phi. Um, this is pretty tough question. I can't really see them asking this again, but I think the easiest way to do this is just going to be to kind of sketch out some points on this solid region, I suppose. But uh let's say rho equals 0, or sorry, phi equals 0, then we're gonna get rho equals 12 because cosine 0 is 1. So we have some sort of 12 here. I don't know. Let's say phi equals pi over 2. We're gonna get rho equals 0. So we have like something like this. And then I don't know. Let's say for the hell of it, phi equals, I don't know, pi over 3. We're gonna get some, I don't know, value like right here. And then, I don't know, let's say phi equals pi over 6, uh, some value here. So, and that's going to be the same on both sides because um, theta isn't given. So it's going to be kind of symmetrical across the x, y axes. Um, so it's going to be kind of something looking like that. My drawing is terrible, but really what it is, I mean, you can really just, I guess, think in your mind, oh, hey, I mean, we haven't really dealt with any other weird regions, so it's going to be some sort of circular region, or spherical, if I do say. So it's going to be looking something like that. And I guess if you plugged in infinitely many points, you would get just that. But it is going to be sphere of radius 6, but instead of centered at 0, 0, 0, it's going to be centered at 0, 0, 6. So I don't know if that's pretty interesting by them, but it's right at our uh, we're going to use spherical integrals, of course, because I mean, we have a sphere. Um, Probably the easiest. And actually, something I do see, um, if we are a little bit, I don't know, smart here, we don't even need to really use an integral just because, I mean, it's a sphere. doesn't really matter where the sphere lies. It's going to have the same volume um, in any kind of location. So we know volume of a sphere is 4/3 pi r cubed, and r is 6. So we can just kind of use this formula. So we're going to get v equals 4/3 pi times 6 cubed. And I don't really know what that is off the top of my head. I have a guess, but I'm just going to write 6 cubed like that. Um, okay. And you can rewrite 6 as just 6 times 6 times 6. This always just helps me. I can rewrite one of the 6's as 2 times 3. So we can cancel out one of the 2's, or sorry, the 3's. And this is a little bit more manageable, I'd say. So I don't know. Let's say um, 8 times 6 is going to be 48. So we have some sort of um, v equals, just I'm gonna leave out the pi. So we have uh, 36 times 4, which is, I don't know, let's see, 144 times 2, uh, 288. So we have 288 pi, and that is answer A. So I don't know. This is more of like a math thing or arithmetic thing. That's what I meant. But um, I think just recognizing that this right here is a sphere just by plugging in some points and saying, oh, maybe they're not going to ask some sort of weird shape. It's not really possible. It wasn't in the course syllabus or anything. So um, I don't know. This is a little bit tricky, but I think it's very possible. Yeah, ironic that this is the third re-recording of this question. And I remember when I took this class, I got very, very similar question wrong. So clearly this question is getting me. But okay, question 8. Calculate the mass of the tetrahedron. Low battery. All right. With corners 0, 0, 0, 1, 0, 0, 0, 2, 0, and 0, 0, 4. That low battery just shows how long I've been re-recording this question. I mean, I'm just kidding, but yeah. Whose mass density is 2z? Okay. So I am going to draw out our regions. So x, z, and y. Um, we have kind of our points right here. This is 0. This is equals 4. This is not the scale, but it'll do. And that is y equals 2. So we're kind of connecting this and making some sort of triangular prism tetrahedron looking region. Okay, so I think we're going to need to calculate or not calculate, but um, write an equation for this plane looking thing. So I'm going to start with z, and I think a trick that's really useful is starting with the starting value of z, or like the max value of z, which is 4 in this case. And then minus, you want to minus some constant times x, and that constant is going to be what it takes based off the value of x that it gave you to get to z equals 0. Because, I mean, this point is 1, 0, 0, so z is clearly 0. And we went up in x by 1 unit, and we went down in z by 4. So if we think about the like slope, we need to go down in z by 4 units. Um, Same kind of concept for y, but y went up in 2, so we only need to go up, or down, sorry, in z by 2 for each decrease in y. So it's just going to be a minus 2y. Okay, so now it's, I guess, the hard part, which I've been struggling with quite a bit, evidently by the low power mode, but triple integral 2z dz dy dx, z is 0 to 4 minus 4x minus 2y. Clearly from this drawing right here, y is going to be 0 to 2 minus 2x, and then x, of course, 0 to 1, because clearly right here is 1. All right, please let me do this correctly. I'm just kidding, but okay. Uh, Keep the outer two integrals, 0 to 2 minus 2x. Integral of 2z with respect to z is just z squared, so we are at 4 minus 4x minus 2y squared, which is really annoying. That is dy dx. I'm going to use a u sub here, so let u be that inside. I'm just not going to write it, but du is going to be, we're first integrating with respect to y, so I'm taking the kind of the partial of u. I'm going to make this a little bit better here, but there we go. I'm so smart. Okay. Du is going to be the partial of u with respect to y. which is just going to be negative 2, or I did that wrong, negative just 2 dy. Great, that is correct. Okay, and now um, let's kind of rewrite our integral. Um, x is still 0 to 1, and now we're in like, we need to take out the constant of 1/2 from the y and integrate u squared now, which is u cubed over 3. So I'm going to take out that 3 and just write it as negative 1 over 6 on the outside. Um, Great. Yep. So now we're at u cubed, um, but we need to rewrite our bounds of u. So if we plug in our um, y bounds now for our u, we're going to get u equals, I'm plugging in just for this. Top bound is going to be 4 minus 4x minus 2 times 2 minus 2x. And if you multiply that out, that's just going to be 0. So our top bound is 0. That is kind of interesting. Yeah, that's correct. And then bottom bound is going to be just 4 minus 4x. So 4 minus 4x. And that is still all 0. Or that is all dx. That's what I meant. So I'm going to actually just rewrite our integral by reversing the bounds and reversing the sign. Like that. Okay, that's just what I like seeing the most. And let's go ahead and evaluate this. So we're still at 1/6. Integral 0 to 1 of 4 minus 4x cubed, all dx. Okay. And here's it's the final part. Hopefully I don't do it wrong, but oof. Now it is time to integrate this. I am belaboring the point, but we are at negative 1 over 24 um, times another 4. Integral, or now we're evaluating the integral, but 4 minus 4x to the 4th power from 1 to 0. Something I see is the 1, if we plug in, we're going to get 0, so that cancels out. And then we do a minus a 4, because we plug in 0, it's going to cancel out. We're just left with 4. So the minus sign is going to drop out. So we're left with 1 over 24 times 4. And notice I am not like multiplying this out because it's probably going to cancel out in the end, times 4 to the 4th power. And I'm going to get 1 power 4 out of here. And that is what we're left with over, let's see, 4 times 6, 4 to the 3rd power. And that is 4 squared over 6, or 16 over 6. 16 over 6. Divide these, we're going to get 8 over 3, and hopefully it's an answer. Yes, it is B. Very nice. Okay, question 9. A potential for the vector field F equals sine y x cos y is what? All right, so if you remember, a potential is going to be some sort of phi of x, y. Potential is a scalar, so um, immediately we can get rid of C because, I mean, I and J implies that it has some sort of vector property to it, which is not true about a potential. Maybe if it's a potential function, it would have been more clear if you didn't know that. But a potential is going to have the property such that the first component of like the force field is going to be the partial derivative with respect to x, and the second component is going to be partial derivative with respect to y. So we could, I mean, solve it out, but I think the guess and check method just works a little bit better. Um, so if we take, I don't know, I'm just looking at the answers here. Partial derivative of answer B with respect to x is just sine y. With respect to y is what? Let's see. Um, that's not it. Okay. Let's see. Question E, or answer choice E, sorry. Partial derivative with respect to x is sine y. With respect to y is x cosine y. So that is our answer here. And I mean, you could kind of integrate it out. So if we have partial derivative of the potential with respect to x is going to be sine y, we can integrate that kind of with respect to x. We're going to get x sine y. And with respect to y is x cosine y. So integrate that with respect to y now. We're going to get x sine y. And remember, these have some sort of constants, right? Um, so we always want to take like the unique terms that we got from integrating, add those up, and then add a constant. And that's exactly what we're doing here. So E is going to be our answer. Question 10, let's see the curve R of t equals cosine t, sine t with t going from 0 to pi over 2, and f x, y, z is just x, y. And then it's asking for an integral of f of x, y, x ds. Believe this should be a z, but maybe I'm wrong. It just looks a little bit out of place because I don't know. This thing should mirror that thing, right? Who knows? But okay, so should be pretty standard. We have our ds equals r prime of t dt. So that's just like the transformation. So let's find that r prime of t. It's going to be a vector, negative sine t, cos t, 1. Take the magnitude of that is going to be, I should make that square root a little bit bigger, but square root of sine squared t plus cosine squared t plus 1. And that is going to be square root 2 by our identity, where this thing right here is going to be equal to 1. So let's go ahead and rewrite our integral. We're going to need to plug in our parameterized version into our f to find f of t. So f, that is a weird looking f. F of t is going to be sine t um, times cosine t. Sorry, times cosine t. So we're going to integrate bounds 0 to pi over 2. I'm going to make that 2 more 2-like, and then um, sine t, cosine t, dt. And then don't forget the square root 2 constant. So we could use u sub for this, but I mean, I see sine t, and then the derivative of sine t is cos t. So we're going to get some sort of, keep the square root 2, by the way, like sine t squared all over 2. I mean, if you differentiate this, you're going to get sine t cos t. And this is from pi over 2 to 0. Nice. So we know sine 0 is 0, so that part drops out. So now we just have sine pi over 2 is 1, so we're really just left with square root 2 over 2. And I think they're playing some trickery here. Multiply by square root 2 times square root 2. We're going to get 1 over square root 2, and that is answer A. It's pretty weird, but okay. Question 11, let C be the half circle x plus y, x squared plus y squared equals 1, with x greater than or equal to 0, then x ds is what? So we have some sort of, this is the region we're concerned with, all of that. And we're looking for x ds, so we need to parameterize that half circle. Yep. So let's do that with, actually, yeah, no, we have to do the half circle. So actually, I'm wrong. We need to not stay in that region. We're just focused on the boundary right here. I was confusing myself, but only the boundary here. And that doesn't really look like a circle, but that does. So the boundary here. Um, so if we get our kind of R of t for parameterization, we're going to get 2 cosine t, 2 sine t, and the 2 is just because the radius is 2 given from there. So let's find our R prime of t. It's going to be equal to negative 2 sine t, 2 cos t. Take the magnitude of that. It's going to be equal to, going to be square root 4 sine squared t plus 4 cosine squared t. And we could factor out the 4, or we're just going to get 2 here. And that kind of makes sense because these like vectors are pretty much equivalent other than the sign, and we know that doesn't really matter in when we take the magnitude. So that's going to be 2. So we can write our integral. Be careful that we get the bounds correct. We need to use negative pi over 2 to pi over 2 because we're starting mean, we could do pi over 2 to negative pi over 2, but I think starting at a negative value from the bottom makes a little bit more sense. We're starting here, which is negative pi over 2, and then we're going all the way up to pi over 2. And I guess this shouldn't matter generally, but if you had like an answer where it has negative or positive, you need to know like the direction. So clearly they don't say it in the problem, so it doesn't matter, but just for future reference would be a good idea to keep that in mind. So we are integrating x ds, so we know x is 2 cosine t. So let's plug that in. Um, could write it just right here, but I'm just going to take out the 4 and just integrate cosine t dt. So that's going to be 4 sine t from pi over 2 to negative pi over 2. And we know pi over 2 and negative pi over 2, it's 1 and negative 1 for sine respectively. So we're going to get 4 times 1 minus a negative 1 or plus 1, or just answer 8, which is C. Cool. And we're done.